Okay, now let's see what the current state of our program is. All the bodies are floating in space and they're acting as they should be. They're colliding with each other and combining their masses, and they're getting attracted to each other as gravity would affect it in real life. An issue with this program is that all of the bodies are going away from the screen. So after a while, this field of view is basically completely empty and all we see is blank space. So to fix this, we need to create a zoom function that zooms as the largest body leaves the screen, because that's the one we want to focus on. The first thing we need to do is have a way to find which body is the largest. To do this, I created a function called findLargest. So what this function does is it has a for loop that runs through all of the bodies in the simulation from 0 to the total objects. Inside this loop, there's a function that checks if the mass of the current object is more than the mass of the largest object. The largest object is stored in an integer variable at the top. It has a default value of 0, but it can be any number that's within the total objects, and since 0 will always be in total objects, it's the safest number to use. Next, we need a function that adjusts the camera to follow the largest body in the simulation. Basically, what we're going to do is we're going to take the largest body and then just adjust the camera by its X and Y direction to center this to the exact middle of the screen. This will in effect make this body look like it's not moving, which may look strange, but it's actually very useful when looking for orbits and will keep the center of attention always on screen. To do this, I created a function called followLargest. In this function, it first calls the findLargest function, which is this one up here. Therefore, then we'll know that the largest variable is the current largest object in the simulation. Below this, we have a variable called xDistMid, which stores the horizontal distance from the center of the screen. To do this, we take the x-coordinate of the largest body and subtract it by the width of the screen divided by 2, which is just the middle of the screen. We will do the same thing for y-distmid, which takes the vertical distance from the center using 1/2 of the height of the screen. Next, we have a for loop that runs through all the bodies in the simulation. Inside the for loop, we update the x and y coordinates of each one of these bodies. Since we want to shift the whole field of view to make the largest object be in the center, we will just subtract the x distance from the middle from the x coordinate and the y distance from the middle from the y coordinate. Once this is done for all of the objects in the simulation, the largest point should be in the center and all of the bodies should act normally. To test this out, let's put it in our run function. To do this, we call the followLargest function under collisions inside the draw function. Here's what it looks like before, and here's what it looks like after. As you can see, this is the largest point, and it looks like it's in the center of the screen. All the other objects are moving around it, and this is very useful because the center of attention is in the center of the screen. Some applications require you to see the motion of all the bodies relative to each other, which this view doesn't really provide. To fix this, we will only center this object once it goes off the screen, so we can see the motion of all the objects at a fixed point without losing sight of data. We will be creating another function called outOfBounds. Inside the function, the first thing it does is run the function findLargest to ensure that the largest value is updated. So imagine this is the screen. To check if an object is in bounds, we need to know a little bit about the coordinate system in most programming languages. Unlike a normal coordinate plane where 0, 0 starts at this corner, in programming 0, 0 starts at this corner over here. Therefore, a point is outside of this box when x is less than 0 or more than the width. A point is also out of bounds if the y value is less than 0 or if a point is more than the height. If any of these conditions are met, that means that the object is outside of the screen. Now, to implement this into our code, we need an if statement. The first condition is if the x-coordinate of the largest body is more than the width of the screen, which would mean that it's out of bounds. These two vertical lines mean an or statement, which means that if either of the conditions on its right or left is true, the function will return true. The next condition that would indicate that the point is out of bounds is if the x-coordinate of largest is less than 0. For the y-coordinates, if the y-coordinate at largest is more than height, it's out of bounds, and if the y-coordinate at largest is less than 0, then it is out of bounds. If any of these conditions are met, the if statement runs. We will just be calling the follow largest function. Now let's implement this into our code by running the out of bounds function. To do this, we just get rid of follow largest and replace it with out of bounds. Here's what it was like before. And here's what it's like after. As you can see, it's kind of hard to see which object is largest because when the screen changes, all of the points change their position. To prevent confusion, I'll color the largest object red and the rest of them white. All we have to do is slightly modify this drawObjects function. After this if statement that checks if the mass of the current object is not equal to 0, we will create another if statement that checks if the current object is equal to the largest object. If the current object is the largest object, we want to color it red. So we will change the fill to the color red, which is just fill 255, 0, 0. Then we will draw the largest body and then revert the color back to white by just saying fill 255. If the object is not the largest object in the simulation, then we will just have an else and then draw the ellipse normally. Now if we run our code, we get one red point and the rest of them white. Even though we always see the largest point, this doesn't mean that we'll see a lot of data. If the point is going really fast in a direction which none of the other points are going, then the largest value will be pretty isolated. Because of this, we need to zoom out when the largest object reaches the end of the screen. This will minimize the effects of the spreading of data once the simulation starts. To zoom out, we're going to want to be zooming out the whole simulation by a scale factor. And this scale factor will change as the simulation progresses and the bodies spread further apart. We will need a global integer variable that stores the scale factor, and we'll be creating it right here. I set the initial value of this variable equal to 1 because when the simulation starts, we're going to be wanting a 1-to-1 scale factor. We will be creating a function called zoomOut to zoom the simulation out. In this function, we'll want to run through all the points. So I'll just copy in this for loop. Then for each point, we want to divide the distance from the center in the x and y directions by the scale factor. These lines right here do this. So the x-coordinate is equal to the distance from the center, which is this part right here, which is the x-coordinate subtracted from the center x-coordinate, which gives you the distance from the center, divided by the scale factor, and then added back to the center point. This gives you the distance from the center divided by the scale factor. The same thing is done in the y direction to divide the y coordinate by the scale factor. Then we also want to divide the mass by 2 so it will appear half the size on the screen. This is done by just dividing the mass by the scale factor, like this. Now that we have a function to actually zoom out the simulation by a scale factor, we need instances where we can increase the scale factor. We will double the scale factor whenever this if statement in the out of bounds function is called. Therefore, the simulation will zoom out by a factor of 2 whenever the largest point is outside of the viewing area. To do this, before calling the follow largest function, we want to set scale factor equal to scale factor multiplied by 2. Let's experiment what happens when we call the zoom out function now. After the out of bounds function, let's call zoom out. Now let's run the program. As soon as the largest point leaves the screen, the simulation rapidly zooms out. This happens because the zoom out function is called every time the objects are drawn to the screen. As soon as this if statement is called and the scale factor line runs, the scale factor is equal to 2. Since zoom out is called every frame, what will end up happening is the simulation will zoom out by a factor of 2 every frame, which results in what we saw before. To do this, we want to reset the x and y coordinates of each point after all of the points are drawn to the screen. This function is actually really easy to make. It's just a slightly modified version of the zoom out function. So first, we'll copy and paste this zoom out function. We'll rename this to reset, and then instead of dividing the distance from the center by the scale factor, we're going to want to multiply it by the scale factor in the x and y coordinates. We'll do the same for mass and multiply the mass by the scale factor. We will run the reset function inside the draw function after the objects are drawn to the screen. The reason why we zoom out and then reset the points, opposed to just halving all the values of each point, which are the xy coordinates, the xy velocities, the xy accelerations, and the mass, is because the gravitational pull between the two objects will be altered. This happens because the relationship between the distance between two masses and the gravitational pull between them is not linear. It's actually exponential. Therefore, objects closer together have exponentially more pull than those further apart. Therefore, when the program is zoomed out, the objects will have more gravitational pull towards each other because the distance between them in the simulation is smaller. The way that we implemented the zoom function in this case is we first calculate all the forces at normal 1-to-1 scale, and then we zoom out and then draw the objects and then reset it. This way, all the calculations of the forces will be exactly as they should be, and it will still zoom out so you can see more data. So when we run the code, as soon as the largest mass leaves the screen, the program zooms out like it should. The only issue with this is that the program zooms out prematurely. As you can see, when this largest point gets to this point right here. The reason for this is that the out of bounds function references the x and y coordinates of the largest point before it zooms out. Therefore, the simulation zooms out whenever the largest object moves out of the viewing area of a 1-by-1 screen. To do this, we'll pass in the x and y coordinates of the largest point after the simulation zooms out. We'll just grab this x and y coordinate code from the zoom out function and put it in our out of bounds function. Now we'll change this value to x coordinate new and change the y coordinate to y coordinate new, and then replace all of these references to a to the largest body in the simulation. Now we will replace the x and y coordinates that we pass into this if statement with x coordinate new and y coordinate new. Now when we run the program, the zoom out function only zooms the program out when the largest body in the simulation leaves the screen of the zoomed out scale factor. At this point, we're done with the simulation, and we should have a working program that we can experiment around with. Thanks for watching.